So in this short video tutorial we will see how to use frequency-dependent structural properties to be used in acoustics, vibroacoustics, in conjunction with the FEMEO solver. So we see here a typical scenario example of panel transmission loss. So we want to compute the loss of acoustic transmission through a structural panel. So let's have a quick look at the model we see here. So we have a structural FEM that contains the actual panel. So here you can see it's a kind of an A-pillar of an automotive car. And you see that here it's composed of two parts, two meshes. So you'll see here indeed 1, 2, 3 layers of meshes. So one mesh on the exterior and one mesh for the interior layer. So in the first round we consider that the whole panel is made of glass. So that's what we see here. And then we see next how to include PVB that essentially contains frequency-dependent properties, and we see how to set this up. All right. So this is the panel, and around this panel then we have the acoustic cavities. So we have acoustic sender cavities, so that's on the side of where the acoustic waves will impinge. So we'll impinge on this side of the fritz, on the side of the panel, and then we have the receiver on the other side. So that's the other part. If I hide here, you also see that it fits nicely with the structural panel. And besides this, we have some microphones here in the middle. Yeah, just in front of the panel. Okay, so that's the setup for the meshes. And we can see also the definition of AML layers. So on this surface for the sender side and on this surface for the receiver side, we have some constraints applied on the structural panel, fixed constraints here. And in terms of the load, so a set of distributed plane waves that impinge on the structural panel. Okay, so this how the model has been set up, and maybe we can have a look here. Distributed plane waves, how this has been done. So essentially you need to select or to define a point, center of the sphere or the semisphere on which the acoustic plane waves are created, and radius does not really matter essentially because the plane waves propagate with the same strength, whatever the distance here. And if I show only the sender, so you see that the impinge on the sender side. The refinement level controls the number of plane waves used for the definition of the diffuse field that impinges on the panel. And here we use a strength of 1 for this example, which does not really matter because in the end what we are interested in is computing the acoustic transmission loss, the ratio of the input power with the transmitted power. Okay, so this is for the general setup. Can get back to this, and essentially that's what it is. Now if we look maybe quickly at the solution, so before editing it we can see that it calls the different objects that I just explained. Here of course you need random subcase. So essentially when you create a subcase, it's not direct frequency, but it's random distributed acoustic plane waves, right? Okay, if I edit the solution, let's have a look. So in the case control, so we request vibroacoustic outputs that are here, some displacement, input power, for transmission loss and pressure transmitted power. So you see that in essence acoustic transmission loss is requested. You enable the input power with an acoustic surface, so that's the surface on which the input power will be computed. And if I only show the sender, you see that we measure the input power on the fluid that is on the side of the sender, the reverberant side, that will impinge on the panel essentially. Then for the transmitted power, we use the AML of the anechoic side and transmission loss to enable this output. Okay, so here we go. Then for sim frequencies, in this example, just a few between 100 and 1000 Hertz, but of course you can modify this as you wish. This is to make the computation faster for this example. And if we look then in the bulk data here, have a free structure interface modeling parameters object, so to define the couplings, and we just kept here the standard default parameters. They ensure proper coupling here. And we activate FEMEO, of course, also using the standard parameters, and so. All right. Okay, and here we've already computed this first solution with only glass, as I described. So now let's modify the structural model to include indeed frequency-dependent material in the intermediate layer. So as we said, we have this mesh for the exterior side of the panel, and here the intermediate layer. So I'll simply move it here under this collector that already contains the PVB. So we see now this is this purple mesh, and if I edit this collector, edit the property, and voila, we'll see here the material that it's referring to. So choose material, and we can edit this material, and we see how it has been defined, and this will explain you how to this will tell you how to define frequency dependent material. So to maybe simplify the UI, since we know that it's frequency dependent properties that you want to define, we can already select this MAT1F subset here, and we see a few less entries. So we can define here the reference frequency, so that's when we have frequency dependent values, we need to have a nominal reference frequency to use the properties at this frequency when we solve for modal response, for instance, because in a modal response we need to compute the structural modes, and to compute the structural modes we cannot of course use frequency dependent values, so we need to have a reference one. So in that case we will use the properties at 1000 Hertz if we would solve for modal coordinates. Then here we define constant mass density, this is its value here, and here is the interesting part. We define frequency dependent Young's modulus properties. So in a sense what you could do is select a field or create a new table. I will just edit the one that I already created, and this is how it looks like. So it's a classical table that you can define in Simcenter, and you can enter here your properties. So you see they are frequency dependent, and you enter the values of your Young's modulus here. Okay, and then you can click OK and just cancel here, and you can plot here your values. So that's what you see, your Young's modulus over the frequency. Okay, and similarly that's what we've done here for the damping coefficient GE. So if I edit again this one, you see that it's also frequency dependent, and we can also plot it here and see it's the curve. All right, so this is essentially what and how frequency dependent material properties can be defined. So this was already available in Simcenter 3D 2020.2, and its usage has been made available for the Femeo solver in 2021.1. Okay, so I can cancel everything so that I keep all the settings that were already defined, and we see then thus the glass as the exterior layers and the PVB material between the two sheets of glass. Okay, so then we can simply go back to our sim, and what we'll do is, well, we don't need to modify anything. Essentially, we'll just clone this solution, rename it, so it's still a solution so 108 Femeo, but here I'll just name it VE as Visco Elastics or frequency dependent. Okay, and I can solve it simply. Okay, so the model setup check ran successfully. That's alright, I can close this, and the solve is in progress. You can see here the solution monitor. Should not take too long. So we see that indeed Femeo is activated. So 108. So let's wait a little bit. Here I also activated multi-processing, so you see 2 processes and 4 threads per process, so total number of threads of 8. And you see that the Femeo solver kicked in. Here at 1000 Hz for the highest frequency, you see almost 100% of the elements use order 2, and this should slightly decrease as we decrease with frequency. 800 Hz, see 92% of order 2, and so on. And you see here at 400 Hz, we're already with 100% of the elements using order 1. Okay, so the solve is done. It was pretty quick. I'll just cancel this, and we can post-process a little bit. Post-process, so here we go. So maybe let's plot first, for instance, this one. So there's a transmission loss for this case with the full glass, so without this intermediate PVB layer. And if we show this one on top with the neuron, with this layer indeed, and we see some changes in the general trend of the transmission loss over the frequency range. So with a higher transmission loss at higher frequency, let's see, maybe here how much, yeah, about 1 dB difference here, and this trend is much more nicely smooth over the frequency range. You don't have also this spiky behavior with the full glass property. So this is a bit what you could observe here, and how you can set up your model with using frequency dependent structural properties for an acoustic simulation with the Femeo solver. So, thank you for your attention.